So we're going to use this video lecture as an opportunity to really solve several problems together and using spectroscopy, and specifically NMR spectroscopy, to figure out the structures of unknown compounds. So these are all problems that are in the new book, the McMurray Organic Chemistry 8th edition, and then I'm going to go through with you step by step how we can use all of the tools of spectroscopy to figure out structures of compounds. So we're going to start this with problem 1321 in your book, and I have a picture of that shown here. So again, this is 1321, and the problem says the integrated proton NMR spectrum of a compound of formula C4H10O is shown in figure 13.7. Propose a structure. So here, let's open ChemDraw also, so that this way we can sort of figure this out together. And I'd say the first thing that we should look at here is that despite the fact that this molecular formula has 10 hydrogens in it, it still has only 2 signals, okay? So it's H10, but only 2 proton signals. And that clearly indicates that we have only 2 types of protons in this particular molecule. So that's the first thing we're going to see from looking at that spectrum, that there are 2 types of protons. And the second thing is, if I look over here at the relative areas of the peaks, I see that they're in a ratio of 1.5 to 1. Okay, so that's about the same as a 3, that's 3 to 2. Although because we have 10 protons, what that's going to mean is we have 6 of one type and 4 of another, okay? So that hopefully is clear to people that the signal at 1.22 ppm corresponds to 1.5 H. Signal at 3.49 ppm is 1 H, but since you can't have non-integer numbers for your protons, what that means is 1.22 ppm is 6 H, 3.49 ppm is 4 H. So, of course, that simplifies to 1.5 to 1. So it's clear, the first thing we can see is that this molecule must be very symmetrical to have only 2 types of protons, despite the fact that there are 10 of them in the structure. So I'm just going to redraw the molecular formula here as C4H10O. Okay, now let's look closer at what the proton NMR signals actually look like. So going back over here, I can see that the signal, let's start with the signal here at 1.22 ppm. That's a triplet, so this is a zoom in of that. That means that it's 1 peak that's split into 3. And what I know from learning about splitting patterns is that signals that are split into 3 peaks, this peak must be next to must be on a carbon whose neighboring carbons have 2 protons on it. I'm going to write that down, okay? So if I'm signal is split into a triplet, that means on neighboring carbons there must be 2 protons available. Okay, and more generally, if a signal is split into n peaks, okay, that must mean that on neighboring carbons there are n-1 protons available. Okay, so if the signal is split into 2, there's 1 proton on the neighboring carbon. If it's split into 3, like in this case, there are 2 protons on neighboring carbons. And again, just to review, what I mean by neighboring carbons is if I'm looking at a proton here, for example, when I talk about neighboring carbons, I mean how many protons are on this carbon, or here, let's put another carbon in, or that carbon. Okay, so that's how I'm defining neighboring carbons, and the number of protons on all of these neighboring carbons together are going to contribute to the splitting of this particular proton. So that's, now I see, looking at this spectrum, I see that there is a signal that corresponds to 6 H's, and all of those 6 H's are chemically equivalent, and they are all next to CH2s. And I know that again, that they're next to CH2s from being split into a triplet. Okay, so let's see. What have I learned about the signal at 1.22 ppm? I've learned already quite a bit. It corresponds to 6 hydrogens, all chemically equivalent, and all next to a CH2 group. And then the final thing is just looking at, and this is sort of where we started proton NMR from, looking at the position of the ppm, so we're defining that as chemical shift in delta. That tells us what kinds of protons, what kinds of environments they are. So this is clearly in the alkane region. Okay, so I'm going to put that in also. Alkane or sp3 hybridized carbons are bearing these protons. Okay, now let's go to this other signal here, down here at 3.49 ppm, and let's figure out what we can learn from here. Now, what can I learn about this signal at 3.49 ppm? A few things. It corresponds to 4H, 4 of my 10. Okay, those are also all chemically equivalent. And let's look at the splitting here. It's split into 4. That means it's next to a CH3. Okay, and I know that because it's split into M plus 1, so it's next to 3 H's. Therefore, it's split into 4. And then finally, I'm going to look at the splitting, at the chemical shift, and say that these are probably also saturated alkanes, but they are next to an electronegative atom. Okay, so let's say saturated alkanes next to electronegative heteroatom. What that does, that proximity to an electronegative atom makes them less shielded. Okay, so let's draw something, what I mean by that. So protons, for example, on this carbon here are going to be less shielded because the bonds, this CO bond is polarized towards the oxygen. Okay, this bond, which leads to de-shielding in the protons that are attached. So I'm going to try to put this picture together now with all of this information that I now know about my molecule. I can put this all together and say, let me draw something that has these characteristics. So I'm going to draw this. And now see, I have an oxygen. Okay, so again, I know this molecule is highly symmetrical, and so therefore that's how I'm going to draw this. It also has no unsaturation in the molecule. Okay, so if you're not familiar, we talked about this in class, how to calculate degrees of unsaturation, but if you need a review on that, please make sure to do so. Okay, so now let's see if I can draw this molecule and whether this solves the characteristics and the criteria consistent with the spectra. So, let's see. First, the molecular formula, C4H10O. So I have 4 carbons, good, 6, 5, 10 hydrogens, and 1 oxygen. So the molecular formula is satisfied. Now let's think about the proton NMR spectrum here. So I have these methyl groups, this CH3 and this CH3. Those are chemically equivalent. They're 6 protons, and they're all next to the CH2s. Okay, so that's going to be, that's going to work in terms of matching the criteria here. So I'm going to make these all now. Let's make these red. These 6 chemically equivalent protons are the signal at 1.22 ppms. Now, let's see about these protons here. Here, let's make these red so they match. These CH2s, well, they correspond to 4H. They're all chemically equivalent. They're next to CH3s. That's what splits them into a quartet. And they are attached, they're saturated alkanes that are attached to a heteroatom. So this works, and this is actually the answer to problem 13.1. And let's just sort of more generally, what I'm hoping that we'll be able to learn the more problems we do is to sort of recognize common motifs in proton NMR. And in particular, when you see a triplet that corresponds to 3 and a quartet that corresponds to 2, that almost always means CH2, CH3, an ethyl group. I'll write that down also. So this particular example has one common motif in NMR, in proton NMR, is if you see a triplet that corresponds to 3H and a quartet that corresponds to 2H, what that almost always means is that what you have is a CH3, CH2, and ethyl group, okay? So then this CH3 is the triplet, and that's a triplet because of its proximity to the CH2. And this CH2 is a quartet, okay, and that's a quartet because of its proximity to the CH3 group. Okay, so that's the problem 13.21. Okay, so let's continue now with problem 1345 in the book. Okay, and this problem, which I've show a picture of over here, says propose the structures for the two compounds whose proton NMR spectra are shown. So let's do the first one, is C4H9Br. Okay. C4H9Br. Okay. Now the first thing, let's look at this spectrum and see what we can figure out. And this one has another useful motif. Let's start with the areas here. So we have 9 protons, that's the H9, and the relative area shows 6 to 1 to 2. So that means right away we have 6 of one type of proton, 1 of another type, and 2 of a third type. That's the first thing. Now, the signal that corresponds to 6 protons is the one at 1.05 ppm. So let's see if we could zoom in here. That signal is split into a doublet. Okay, so the 6 chemically equivalent protons are split into a doublet. That means they are next to one other proton. Okay? So again, they're split into 2. That means they're next to, on adjacent carbons, something with 1 proton. And this is another common motif, so that almost always means a situation like this. So let me show you what an isopropyl. So this is another common motif where I have a situation like this, where, hold on, put the H there, and then here that'll be just the rest of the molecule. So a doublet that corresponds to 6 protons, that's very close to TMS, very low ppm, almost always means this group called an isopropyl. So I have these 2 methyl groups are chemically equivalent, so they give me one signal corresponding to 6 protons. And because they're next to a carbon with 1 H on it, that splits them into a doublet. So this is another common motif. A doublet near 1 ppm corresponding to 6H means isopropyl group often. Now let's see what else we can do here. Now, if I look now at the signal that corresponds to 1 proton at 1.97, and here they've shown the zoom in of that region, I can count 1, 2, 3, 4, 5, 6, 7, 8, 9 signals. Okay, so that's 1 proton that's split into 9. That means, so this is the 1.97 ppm signal, is 1 proton next to 8 others. Now, if I go back to my isopropyl group as my core, that means that almost certainly refers to this proton. Okay, and this proton is next to, the way I've drawn this, 6 carbons with 6 protons. Okay, so these 2. But in order to get a signal that's split into 9, it has to be there have to be 8 protons on adjacent carbons. So now if I go ahead and I draw something like this, okay, I now add in another carbon with 2 protons, with thinking only about the proton that I've highlighted in red, I can count how many protons are attached to adjacent carbons. So this carbon, the one bearing the H, has 1, 2, 3 carbons adjacent to it. And if I add up the protons on the adjacent carbons, I can count 3, 6, 7, 8, which means that this red proton is split into 9. So that's what I see. And again, these methyl groups are split into a doublet, okay, by this H, so that I see that as well. And then finally, these two H's over here are going to be split by the proton on the neighboring carbon. So the way I've drawn this, there's only one neighboring carbon with a proton on it. So these should be split into a doublet as well. And if I go here, I look at the signal now at 3.31 ppm, I can see that they are in fact split into a doublet that corresponds to 2. Alright, and now what I'm going to do is just add the bromine at the end over here. Okay, and the reason I know that the bromine has to be over there rather than any other place in the molecule is these protons, so let's give them a nice color. Okay, let's find, nope, only these. These protons, these blue protons, are split only into a doublet, which means that their neighboring carbons can include only one proton on it, okay? So this part, this other linkage on my carbon, can't have any protons directly attached to it, or else that would cause further splitting in the blue protons. Alright, so knowing my molecular formula C4H9Br, and being able to assign that doublet near 1 ppm to these, the 9 split thing corresponding to 1 proton is the red, and then my other doublet, which is less shielded because of its proximity to the bromine, corresponds to the blue protons that I've shown over here. Okay, so that's 13.45, question A. Now let's move on to question B on 1345. Alright, let's see if we can do this now. That says C4H8Cl2. Okay, great, let's do this guy. Molecular formula I'm going to put over here, C4H8Cl2. Okay, first thing, I have 8 protons, and if I go to my relative areas, 3, 5, 7, 8. Okay, so these areas are good. And I also see I have 4 different types of protons, so let's write that down. 4 types of protons here. And now let's see if we can figure out the structure of this molecule. So again, I have a doublet corresponding to, at 1.56 ppm, that corresponds to 3 protons. Here, so let's go through each signal now. 1.56 ppm, doublet for 3 H's. Okay, so that means that that's probably a CH3 next to a CH. Okay, let's start with that information. Now the signal at 2.13 is split into 4. Okay, so let's write that down. 2.13 ppm is a quartet for 2H. Okay, that's probably a CH2 next to a CH3. Now let's see what else we can find. At 3.72 I have another, I have a mess it looks like. 3.72 looks like a mess. So let's skip that for now. And 4.25, I guess that's another mess. I think they're all quartets. Maybe they're all quartets, guys. Alright, let's see. Hold on, what we can draw for this particular structure. Alright, let's continue. So just going back to the signal at 2.13 ppm, it's a quartet for 2H. That means that there are 3 protons on adjacent carbons. Okay, now at 3.72 we see pretty much a multiplet. Okay, that's a mess. 3.72 ppm, we're going to see a multiplet for 2 H's. And at 4.25 we're going to see, let's check out what we see at 4.25 ppm. It's another case of a multiplet. It's another multiplet. This is for 1H. So let's try to put this together. I have 4 carbons here and a pretty non-symmetrical molecule. Okay, so I'm just going to start by drawing a 4-carbon chain. Now I know that I have 1 CH3 group. Okay, that's the 1.56 ppm. So I'm going to right away put in that CH3 group. And that's a doublet. Okay, so that means that on my adjacent carbon, I have a single proton. Okay, and instead of having two protons, I'm going to use that as an opportunity to put one of my Cl groups right in there. Okay, and now let's see, I have, this is going to be my 1.56 ppm signal. ppm signal, okay. This H over here is going to be my one proton signal. We're going to do that the 4.25 ppm signal. Okay, and that makes sense because it's equivalent to only one proton, and also it's pretty d-shielded because of its proximity being on the same carbon as the chlorine. Okay, now let's continue with the rest of my molecule. I'm going to put, I now have 2H, 2H, okay, so I'm going to put 2 H's on each of these. Alright, and now 2H, 2H, and then I have the Cl group over here. Okay, and I can go back to my NMR spectrum and see if that structure makes sense. So again, I can see, let's see if we can zoom in so we can look at both of these at once. The signal at 1.56 ppm, that's this CH3. The 4.25 is this H. Okay, this CH2 is going to be at 2.13, and then this CH2 here, which is closer to a chlorine, is going to be less shielded. Okay, so that one's going to be at 3.72 ppm. Okay, and again, this CH2 is going to be at 2.13 ppm. Alright, let's move on now to do a problem in carbon NMR spectroscopy, okay, just for a change of pace here. So this is 13.51 in the textbook. And if I go to, okay, look at the spectrum, the question is assign as many of the resonances as you can to specific carbon atoms in the carbon-13 NMR spectrum of ethyl benzoate. So here I'm going to redraw ethyl benzoate here so we can talk about it. The first thing I would say is carbonyl carbons, okay, so the carbons that are directly attached to a carbonyl, those have pretty characteristic peaks in the carbon NMR spectra. Those are way de-shielded. Those are always the least shielded ones. So when I see here this peak at like 165 ppm, something like that, I know for sure right away that's my carbonyl carbon. So here, let's put that one in. Sorry, 165 ppm. Okay, now I look at the aromatic region and I can count 1, 2, 3, 4 peaks in the aromatic region, okay? 4 peaks in the aromatic region, and I can count how many different types of aromatic carbons I have in this particular structure. I can see 1, okay, and then these two are chemically equivalent to each other. These two are chemically equivalent to each other, and this is a different one. I'm going to put numbers on this structure as well. So the question now that we're addressing is how many types of aromatic carbons do I have? Okay, so what's the chemical equivalent in this benzene ring? And I can see, okay, that these carbons, carbon 2, are chemically equivalent. The carbons that are carbon 3s are equivalent to each other. And this carbon 4 is different from the other ones. And you can do this if you wanted to swap in different atoms, different X's or whatever for this molecule. One way to think about it in terms of figuring out chemical equivalence, and I've gone through this with a couple of people in my office hours, is looking at the symmetry of the molecule. So this molecule, if you can have some symmetry through this benzene ring. So here, let's think about it this way. If instead of looking at that ethyl group or that ester directly, if I just replace this sort of with a generic R group and focus on this benzene ring, I can draw a plane of symmetry right through this molecule, making, again, these two chemically equivalent, okay? And then this one different because it's directly attached to the R group, and this is a fourth category now because it's opposite from the R group. Alright, so that's, I'm also going to introduce some terminology here, and this is going to come up when we start talking about electrophilic aromatic substitution reaction. The carbon 2s, okay, are called ortho to the thing attached, this substituent. Carbon 3 is called meta, and carbon 4 is called para. It's a way of talking about substitution patterns, okay? So again, thinking about a benzene ring with one thing attached to it, these two carbons are called the orthocarbons. These two are called the metacarbons, and this guy here is the paracarbon. Okay, so that's 4 types of carbon atoms on this aromatic ring, and that corresponds to 4 signals in the aromatic region. So I just want to make a few notes here so we don't get confused. The first thing is that you cannot integrate carbon 13 NMR peaks, and the same way, conversely, the heights of the peaks do not correspond to the number of carbons. Okay, so here I have 4 peaks. Some of them are tall, some of them are not tall. Offhand, I can't say which ones correspond to which carbons in the spectra, except to say, okay, with one exception, I can say just sort of qualitatively, quaternary carbons give the weakest signals. Here, let's zoom in on that. So that's just a qualitative thing. They get the weakest signals from things with no protons attached to it. Okay, but again, 4 peaks in the aromatic region, 4 types of carbons in this molecule. That works for me. Now I have 2 other signals in my molecule. I have this peak just around 60 ppm and the one around 15. Okay, so these are both alkane-ish peaks, sp3 hybridized carbons. One of them is substantially less shielded, and in this particular case, that's going to be the carbon that's directly attached to the oxygen. So this CH2, this C, is this peak, and the one that's most similar to a regular alkane without deshielding or less proximity to the electronegative atoms, that one's going to be over here down at 17 ppms. Okay, so that's as far as question 13.51 goes. Okay, we're going to move now to 1358, question B. Okay, so the question for this problem is propose a structure for this compound. Okay, the molecular formula here is C7H7Br, okay? And when I look at this compound with 7 protons, I can see that the areas for my 3 different signals, so 3 types of protons, are in the ratio of 1.5 to 1 to 1. Okay, so right away I'm going to make that 2.31 ppm is now 3H. Okay, 7.01 ppm is now 2H, and then 7.35 ppm is also going to be 2H, okay? That's 7 protons. Instead of 1.5 to 1 to 1, I just multiply those areas all by 2 to get 3 to 2 to 2. Now, the second thing I want to notice is I have 2 types of protons in the aromatic region, so in the 7 ppm area. Okay, and those 2 types of protons are each split into a doublet. So this is going to be a third motif that I hope people will start to recognize is 2 doublets in the aromatic region equals para-substituted. Okay, so we talked about ortho, meta, and para just in the previous problem. Okay, these 2 doublets are para-substituted, indicate a para-substituted aromatic ring. That means I have a benzene ring with 2 things attached to it, one on this side, one opposite, that's the para. And the reason that translates into 2 doublets in the aromatic region is here. Let's draw these. Hold on one second. Let's see if we can draw these in a nice pretty color. This, and I want this to be red. I don't know why it's not red. Sorry guys, hold on one second. Let's see. So H's, let's put on these H's. Good, H, good. Let's make that guy red. Good. These 2 are chemically equivalent. And then these 2, which I'm going to put in blue, are chemically equivalent to each other. And the red guys split the blue guys into a doublet. And the blue guys split the red guys into a doublet. Okay, so that's how a para-substituted, where I have one thing over here and one guy over here, how that leads me to 2 types of aromatic rings. of aromatic protons, each of which are split into a doublet by the other set of chemically equivalent protons, okay? So that's the first thing. Every time you see a doublet in the aromatic region like that, every time a pair of doublets, you should think to yourself, that is a para-substituted situation. So that automatically makes this easier for me to figure out the structure of this molecule by knowing that I have one thing over here and a different thing over here. I've already accounted for a benzene ring. And finally, the fact that I have a 3H signal at 2.31 ppm, and that's a singlet. Okay, that singlet means that it's not next to any other carbons with protons, okay? Means that I can put a methyl group right over there, and that would solve the criteria of that signal at 2.31 ppm. And then finally, just to account for what's going on in this molecule, I can put the bromine over there. So I should also ask myself now which H's, whether my blue H's or my red H's, which of those corresponds to the signal at 7.35 and which one corresponds to the signal at 7.01. So I am going to give an opportunity for extra credit here. Okay, so here, let's write this down. Apologies for the confusion around the extra credit last time. I will give 3 points. No, sorry, I'll give 2 points. Sorry, I'm feeling 2 points extra credit today. Which set of signals corresponds to the peak at 7.01 ppm? Which set of protons corresponds to the peak at 7.01 ppm? And which set of protons corresponds to the peak at 7.35 ppm? And with a coherent explanation of this, and emailed to me by 8 a.m. on Wednesday. Okay? So again, apologies for the confusion around last time's extra credit. This time, you can get up to 2 points for telling me which set of protons, the blue or the reds, correspond to the peak at 7.01, and which set corresponds to the peak at 7.35, with a coherent explanation, emailed to me by 8 a.m. on Wednesday, February 11th. Great, now let's move on to the next problem, which is 13.58, question C. Hold on, let's get some more. Fine, we'll do it here. Okay, so now let's look at C. So this is 1358C. We're trying to figure out the structure for C8H9Br. Okay, let's draw that here. And we certainly have signals in the aromatic region, so I'm going to start by drawing a benzene ring. One thing I can see for sure, especially comparing these guys to the signals up here, is that this is definitely not a para-substituted aromatic ring. So let's write that. Not a para-substituted aromatic ring. And let's see, if I have 9 protons in the molecule, and I have 1, 1, 1, and then 1.5, let's put this as 2H, 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 3H. Is that going to work? Yep, so that's going to give me 9. Okay, so that's good. And then the second thing I'm going to want to figure out here is, so now I have 5 protons in the aromatic region. Okay, that's the, okay, let's write the ppms here as well. 7.18 ppm is 2H. 7.29 ppm is 3H. 3.16 ppm is 2H, and now 3.56 ppm is also 2H. Okay, so I have 5 protons in the aromatic region. That means I'm only going to have 1 substituent attached here, and all of these 5 are going to be the H's. Okay, and now, so let's put in those H's as well. Put in those guys here. Okay, so now I have 4 other protons, 2 sets of 2 protons each at 3.16 and 3.56. Let's look at that splitting pattern. I see these are each triplets, okay? So I have 2 triplets, 2 sets of 2 protons, each is a triplet. What that means is that each one is next to a CH2, and each is also equivalent to a CH2, so that means I have a CH2CH2. Okay, I still have a bromine here in the molecule, so what I'm going to do now, in order to get 2 sets of CH2s, is set up the structure this way, CH2, CH2 bromine. Okay, so these H's give me a signal corresponding to 2 protons, and they're split into a triplet by these 2. And then again, these 2 H's are split into a triplet by these guys over here. So this CH2CH2Br pattern gives me 2 triplets, each of which integrates to 2 protons. So that's how I get the correct structure on that section. And again, the aromatic ring, I see I have 5 protons in the aromatic region. That means I have a mono-substituted benzene ring with 5 protons and 1 substituent, and that's how I end up with this structure for 13, again, 0.58, question C. Okay, we're going to do question 13.61 now, so I show that here. I hope it's clear enough. We're trying to figure out the structure for compound C. Okay, the mass that we have is 86 in its mass spectrum. We have an IR at 3400 wave numbers, and this carbon-13 NMR data. Okay, so the first thing we're going to figure out from the IR spectrum is that we're talking about an alcohol. Okay, so this is now 13.61. This molecule has a mass of 86 AMU and an alcohol. Now let's look at the carbon spectra here. We have, here, cool, 1, 2, 3, 4, 5 peaks in the carbon spectrum. Okay, so regular carbon NMR spectra is showing me 30.2, 31.9, 61.8. Hold on, we're going to draw this like this. 30.2, 31.9, 61.8, 114.7, 138.4. Okay, so that's 5 types of carbons, and because the mass is 86 AMU, that probably means I actually have only 5 carbons, so it's not a particularly symmetrical molecule. I can see these two, the 138 and the 114, look like they're alkenes. This one looks like an alkane near an OH. This is a regular alkane, and this one will also be a regular alkane. So that's the first information I can get from here. Now we're going to go to the depth experiments shown in the particular problem. The depth 90 experiment shows a signal at 138 ppm. Okay, so that signal now is showing me, so depth 90 signal shows me a CH group. Okay, so I'm going to put that information in as well. This is a CH group according to depth 90. Okay, now I go to the depth 135, and the depth 135 shows me a positive peak at 138. Okay, so that's good. That's a CH group. That confirms that. And then all my negative peaks in the depth 135 mean CH2 groups. Okay, so this guy's going to be CH2, this guy's going to be CH2, this guy's going to be CH2, and this one's going to be a CH2 as well. So now, knowing everything that I know about this structure, I'm going to start by just drawing 5 carbons. Okay, a 5 carbon chain, 1, 2, 3, 4, 5, good. I know I have an alkene somewhere in the molecule, and that alkene has both a CH and a CH2. Okay, so the fact that that alkene has a CH2 means that I'm going to put it at the end of the 5 carbon chain. Okay, so that's how I can ensure that I have an alkene carbon that is a CH2. That alkene also has a CH on it. Okay, and then in terms of the rest of my molecule, I'm looking at 3 CH2s. Okay, so in order to get 3 CH2s, I'm going to put the OH way at the end over here. And now let's just figure out if that gives me the correct structure. So I have now 3 CH2s, and I can figure that out from the DET, again, carbon experiments. Okay, so this signal, let's go through this. This is an alkene, that's a CH2, that's 114 ppm. This is an alkene, that's a CH, that's 138 ppm. This is a regular CH2, okay, so that would be the 31 or the 30. This one is a regular CH2 also. And then this is a CH2 next to a heteroatom, this OH. Okay, so that's going to be the 61 ppm signal in the carbon NMR. And then finally, let's just confirm that I have the right molecular weight. So here I see 86.13 grams per mole. So that's how I know that this is the correct structure for 13.61. Okay, we're going to do one more problem here. So this is going to be 1362. Hold on, let's pull up. Okay, so this is going to be the problem that we end with for today, is 1362. And that question says that compound D is isomeric with compound C. So that's the structure we just figured out over here. But it has slightly different carbon-13 NMR data. Okay, so let's see if we can figure out what this means. Okay, let's do now compound D file. Let's give us a little bit more space for this. Okay, now let's see. In my regular carbon NMR spectrum, I'm looking at 9.7, 29.9, 74.4, 114.4, and 141.4. Okay, now let's figure it out. DEP 90. Okay, so the DEP 90 gives me, again, the CH signals here, gives me peaks at 74.4. So that's a CH. And then 141 is also a CH. Okay, now the DEP 135 positive peaks are giving me, those are my CHs or CH3s. Okay, so now the 74.4 is a CH, so is the 141.1. That 9.7, which is a positive peak in DEP 135, but did not show up at all in DEP 90, that's a CH3. And then all my negative peaks in DEP 135 are CH2s. So I have a CH2 there and a CH2 here. So again, let's see if we can put this together. This is, here, let's put in the functional types. Alkane, alkane, alkane near OH, alkene, and alkene. And I know these characteristics by looking at the table in my book for carbon NMR spectroscopy. Let's draw a 5-carbon chain here. 1, 2, 3, 4, 5. I have again an alkene that has both a CH and a CH2, so I'm going to automatically put that alkene near the end of my chain, so that gives me a CH alkene and a CH2 alkene. Okay. Now as far as the rest of my molecule, I have a CH, a CH2, and a CH3. Okay, so to try to figure out where that goes, I'm going to put the OH guy right over here. That gives me a CH alkane, and that also is going to give me a CH2 alkane as well as a CH3 alkane. And again, final check, I'm going to just look at the molecular weight of my compound, see that that's an isomer of the compound that I found in the previous problem, and conclude that that's in fact my structure. Okay, so in general, I really hope that this online lecture has helped you figure out structure determination by NMR spectroscopy. I'm going to do I'm going to try to make some more videos, again, illustrating how I go through these problems sort of one step at a time, and hope that that helps figure out and clarify problems for you.